Welcome everyone. I mean, we have several more seconds, but I just want to use this time for some informal chat before we officially start. I mean, it is good to see all of you, and whoever is having a good connection and wants to share his video is more than welcome. But during the presentation, at least during the questions. I am opening officially the second session of the second extragalactic astronomy session, and I am really proud to chair this session. We have really like I have to say superstars presenting talks. All of today's speakers are really famous and well-known astronomers and with some good results and amazing results and amazing achievements, not just in research but also in making a difference in astronomy and developing astronomy. I am very pleased to welcome our first speaker, Professor Deborah Siatki, who is a reader at the Institute of Astronomy at Cambridge, University of Cambridge. And she's going to give a talk about supermassive black holes in all their guises. And I will give you a reminder 5 minutes before, and we'll leave a couple of minutes for questions. So I will give a reminder after 30 minutes if you agree. Okay, thank you.
Okay, thanks very much. So can you hear me? Can you see my screen? Okay, yeah.
All is cool.
Okay, great, thanks. So it's a really great honor and pleasure for me to be talking. Sorry? I just didn't hear that bit.
All is good. Maybe there was some echo.
Okay,
All is good.
Somebody else was talking. So it's a really a great honor and pleasure for me to be telling you today about the research I have been doing recently. And the only shame is that I cannot be present in Belgrade, in our beautiful Belgrade, but I hope that will happen on a next occasion. So in this talk, I will tell you a little bit of an overview about supermassive black holes, especially in theoretical models, and where the field stands and where we are heading in the near future. So I want to start with basically the current state of the art in cosmological hydrodynamical simulations of structure formation. And I just want to start with this kind of really simple sketch, but I think it's very useful to set the stage. So we essentially would like to, in these galaxy formation simulations, we would like to simulate a representative sample of the universe on fairly large scales, because like this we can compare in a statistically meaningful way with observations. And just to give you an idea, that is something like the chunk of the universe from one of the simulations I have been involved with, the Illustris project. And typically there we are talking about the scales of order of 10 to the 9 parsecs. But obviously, if you are interested in galaxy formation, we want to resolve the galaxies that are embedded in this cosmic web. And then we are talking about already much smaller spatial scales of order of a kiloparsec. But then it's immediately clear that if we want to study the properties of these galaxies and make some predictions for the current and future observations, we have to understand the inner workings and the inner structures of these galaxies. And this is, especially if you think about star formation, is regulated on the scales of at least giant molecular clouds, which are again much, much smaller, order of 10 to 100 parsecs. And then another very important ingredient are the massive stars and supernovae that again happen on much, much smaller scales, so that we are going many orders of magnitudes down. And ultimately, as majority of my talk will try to highlight, we have to worry about supermassive black holes in the centers of galaxies, where the physics, the accretion physics and feedback physics from these compact objects occurs on really small scales of order of 10 to the minus 6 parsecs or so, obviously depending on the black hole mass. So how do you do this all together? it's very difficult, and especially because all these bits of physics that I briefly mentioned, they mutually couple to each other. So we have a really vast range of spatial scales, and we have a nonlinear physics that couples across this vast range of scales. So ideally, what we would like to do, this is from the first principles, and this is currently impossible, and it will be impossible for a foreseeable future. So what we can do is essentially to try to simulate all these physical processes on a dynamical range that we can resolve. And below these spatial and mass scales, we have to invoke something that is called the subgrid models. And these are essentially some simplified analytic empirical models that often have some ill-constrained or free parameters that we have to then match to observations that essentially treat the physics below the resolution that we can achieve. But even if I would be given now the best futuristic supercomputer that will exist maybe in 50 years, I would still have to live with the subgrid physics, I'm afraid, even if I could resolve much more the spatial and mass scales and extend the dynamic range than it's currently possible. And that's because the physics that governs galaxy formation is inherently extremely complex, and we don't have the answers to many of crucial questions. For example, how stars are formed and exactly where they form, what is their efficiency, how does it depend on the local or more global environment. So these are kind of the big, tough questions that are going to stay with us for a while. So now coming to the supermassive black hole feedback directly. So there has been a couple of years, 4 or 5 years ago, there has been quite some progress in galaxy formation simulations. There have been several independent groups that have used different codes and run their own different simulations to try to reproduce the diversity of galaxy morphologies across cosmic time. And what is really interesting, what all these groups found independently, such as the Lastris project, the Eagle project, Horizon AGN, Magneticum, and more recently there are several others, such as Lastris TNG and so on, and New Horizon. So they have all found that at least at the scale where, of massive galaxies, it is necessary to invoke some strong energetic feedback emanated from supermassive black holes that we think that reside in the center of massive galaxies to regulate the star formation rate, stellar masses, and so on of this massive population. And this is, for example, nicely shown if you look at the bottom plot and the Horizon AGM project. What they have done here, they have performed the same simulation twice, once with AGN feedback, which is shown in these first sets of rows, and once without. And then they have matched the exact same objects living in the same dark matter halos. And what they found, if you don't have AGN feedback, you reproduce these very extended spiral looking massive galaxies that are order of magnitude or more massive than anything that is observed in the local universe. And only with a strong AGN feedback, you essentially quench these galaxies and reduce their stellar masses and transform them in so-called red and dead ellipticals. So that's a very strong hint from this numerical experiment that we have to worry about supermassive black hole feedback. So I want to now step back for a second and tell you a little bit how actually to model this in galaxy formation simulations, because it's a rather complex thing. And the best way where to start is obviously to start how black holes form in the first place. So this is what we call the black hole seeds. And I just want to highlight here the seminal paper from Martin Rees back in '84 that has outlined really a variety of complex channels. Obviously, I won't go over this flowchart in any detail because it would take the whole talk, but essentially to tell you there are many different ways in which it's possible to generate the supermassive black hole seeds in the early universe, and people are actually still debating one channel versus the other. This is still a very active field of research and the questions haven't been settled. So now going a little bit forward in cosmic time. So once we settle on some model, how the first black holes form in the universe, so we don't have to think of anymore about the seeding part, but then we have to think about that these black holes actually live within nuclear clusters, which are embedded in small or more massive galaxies. And these galaxies are going to get their gas through accretion and mergers. So then we have to worry about how this gas then eventually is funneled all the way to supermassive black holes, how they grow in mass, and how also they merge with other black holes. So this is all a very complex hierarchical process, and this is what we are trying to put in our cosmological simulation models. Now focusing for a moment of cosmological growth of supermassive black holes by accretion, which we think that is a main mechanism by which the majority of black hole growth is acquired. There is a really funny cartoon from a famous conference that was here in Cambridge in '79 from McRae, talking about the accretion process and mapping it onto people's idea of how to write papers in astronomy and publish them, and when they have conflicting views, what to do about it, as shown here. But apart from a joke, we have made quite some progress about understanding the accretion process, but again, there are still many fundamental questions. So now being slightly more specific, why is this hard to do? Because we have to again think about a whole range of physical processes occurring on a vast range of scales. So we have to think about black hole fueling from large to small scales, which is going to be very sensitive to the environment. So schematically, again, I'm not going to go to too many details here, but you can separate it into more secular type of processes where it may happen in isolated or weakly interacting galaxies, perhaps parallels, Seyfert-like objects, or you can have different set of processes that happen in more significant mergers, including major merger of galaxies. And then on a relatively large scales of the galaxies themselves, you have all sorts of gravitational torques, or you have the hydrodynamical torques. There are bars, there are M1 modes, and the whole game is here to understand how is the gas angular momentum lost and how gas can be funneled towards the central region where the supermassive black hole resides. On smaller scales, there are different types of torques. For example, there are from nested nuclear bars, which are often observed. There is dynamical friction we have to worry about, all sorts of feedback processes induced by star formation, and also due to the violent relaxation in case of merging, there is also gravitational torque generated that can extract angular momentum outwards. And finally, when we come to the very small scales, ultimately we enter very often in the self-gravitating regime, which is extremely hard again to understand. And finally, we come to the accretion disk itself around supermassive black holes, where we then have to think about effective viscosity in this accretion disk, about MHD torques, the warps in the disks, and ultimately all sorts of type of outflows that I will come to talk about in a second that can interact with this accreting gas as well. So this is essentially where the complexity lies in the thinking about the accretion processes. In terms of feedback, things are not much easier. Again, we can try to put it in some schematic connotation to make it kind of a little bit easier to digest. And people often talk here in a bit of buzzwords. They're so-called the quasar mode and the radio mode. So the quasar mode, what people usually mean is that the black hole is accreting at relatively high Eddington ratio. So it's supposed to be in radiatively an efficient regime. And we think that the accretion disk around supermassive black hole is something like Shakura-Sunyaev disk or a slim disk. And in that case, the feedback may be coming from the inner winds that can be either powered by radiation pressure or can be powered by the magnetic fields. And then on the larger scales, people often talk about different type of outflows or wind solutions. And there are three kind of famous scenarios. One is the radiation pressure driven outflows, one is the energy driven, and one is momentum driven outflows. And of course, this is a massive simplification to the diversity of physics that is happening here. And I just want to highlight that even when the accretion rates are relatively high, there are obviously FR2 sources and jets. And very recent GRMHD simulations have actually found, when they finally managed to increase the resolution and simulate for the first time relatively thin disks, that actually jets are also produced in their simulation cell consistently in these setups. Then if we turn to the radiatively inefficient regime, so low Eddington ratios, then usually the situation changes. The disk structure is supposed to change, perhaps through a truncated disk towards something like a ADEF or ADIOS type of disk. And then again, there can be inner wind that is driven by from the accretion disk itself. But here it's really has been very well established through GRMHD simulations that there is a collimated outflow driven by the magnetic fields, the so-called Bluntfeld-Naik jet mechanism, and that powers rather powerful jets. And then how these jets energetics transfer to the surrounding medium is yet another question. I will come back to it in a second. So now that I told you about how the whole physics is really, really complicated, I will tell you how simple we treat it and why we should try to do better. So I just want to, this is kind of very on a critical side of things, but it's good to have a stand back and look at things. So now I want to tell you about these caveats or issues in cosmological simulations. So regarding all the points I covered so far, so majority of the models in the state-of-the-art simulation, they assume a very massive supermassive black hole seeds. Obviously, this is much easier numerically, but also it helps kickstart the black hole growth in the early universe and help us build us this population of high-redshift quasars, which is not so easy to obtain. And also, majority of models assume that every massive halo has a supermassive black hole seed. This is really theoretically ill justified, and again, it is helping to build up the supermassive black hole population. Then one really big assumption of cosmological simulation is that the accretion model is typically to assume to or occur through some Bondichoid-like accretion, so it's just the spherically symmetric flows. And obviously that helps to kick start the black hole growth and reach the Eddington limited accretion. But what is really problematic with this assumption is I have just been telling you there is the angular momentum, there are the torques, we have to get rid of angular momentum, we have to have the gas funneling to small scales, there is the accretion disk. So we are pretty confident that the spherically symmetric accretion models, they are maybe applicable to a very small fraction of real situations. So this is not, cannot be applied generically. It's a too strong an assumption. And then coming to the feedback processes, there is various interplay here between the feedback process from black holes and actually from star formation. And often complex star formation feedback processes are neglected, which could clear the gas surrounding the black hole seed, for example, and that could affect its initial black hole growth. But also, majority of models talking about AGN feedback specifically do something that we again called in a buzzword a thermal dump. So this is just releasing some amount of thermal energy, some amount of energy we think it thermalizes effectively through the gas. So now that I have been telling you about the inner winds that are radiation, pressure dominated, or magnetic fields or jets, obviously this is again massive simplification. And finally, an important point, why is this so simple? Because spatial resolution, as I told you at the beginning of the talk, of these simulations is very limited, and it's at best of order of hundreds of parsecs, and with some zoom in techniques we can do a little bit better. And then the question is how we can capture the relevant physics when essentially we coarse grain these simulations so much that we cannot resolve all these processes that matter. And finally, just a little critical word is often in the literature, the different subgrid models, they achieve very similar results because they want to match some set of observations that are very favorable in a given point in time. And then one can ask what is the predictive then power of this cosmological simulation, how much fine-tuning is involved, and ultimately how do we learn about the physics, because that's what we care about rather than just fitting the observation. So we have to try to break these degeneracies and understand actually how to constrain physical processes instead. So let me now tell you about each of these bullet points that I highlighted as caveats, some recent developments, and how maybe some of these points are more important or less important, and how results change when we relax some of these assumptions. So again, I start with the seeding bit. This is a recent work led by my postdoc, Colin de Graaf. So what we have done, we have taken the illustrious simulation that I briefly mentioned before, and we have devised an algorithm that we can post-process this simulation. Essentially, at each time step of simulation, we can recalculate the whole black hole growth and merging histories, and where we can change the seeding models rather than the default models assumed in the illustrious simulation. So we can change the fraction of where the black holes is seated in how many halos. We can actually incorporate more realistic models where we can track the black hole, for example, where the black holes are formed depending on the local gas properties. We can check for the gas content, angular momentum, metallicity, and try to follow some prescriptions how people think that, for example, in the direct collapse scenarios, black holes form. And I just want to highlight, once we play this game and change the seeding prescription, but then don't change anything else, so leave the accretion and feedback the same, how much do the results change? And actually the changes are quite significant. So first I wanted to show you a little bit of black hole scaling relation. So this is black hole mass plotted versus the proxy for the bulge mass of the host. At high redshifts, the red, always the red contours indicate the original illustrious simulation, and the field colored histogram show this new model motivated by the direct collapse scenario. So you can see at high redshifts, the results look very similar. But then as we move to lower and lower redshifts, going towards the top of these panels, I hope you can see my mouse pointer. Then what we see that at the high mass end, where majority of black hole growth has happened through accretion, so it's kind of the memories lost from the seeding process, results are very similar, but at a low mass end, there are massive differences. Because in this direct collapse model, you just don't continue seeding throughout the whole cosmic time, but when the galaxy becomes metal enriched, you stop seeding, to say it in a simple words. Essentially, you lose a significant population of black holes in low mass systems. So it means that the results are sensitive to the seeding prescriptions, and quite significantly. We can quantify that through the black hole mass functions and luminosity functions. I won't go into details of this. I just want to say the highlight. We will have to wait for Athena to try to break these degeneracies, because we have to probe quite a faint end of the luminosity function to be able to distinguish different seeding models. And this will be possible both at low and high redshifts to do. So there's these different colored lines are showing different models. And there is a promise that we can learn something about the seeding, but not in the immediate future. So another interesting thing is obviously, if you think about the future, is obviously LISA. That's a really big thing. We are all looking forward to the ones that work in the supermassive black hole community. So, and there, given that we have with the seeding affected the occupation fractions of black holes, we obviously are affecting how many black holes merge with each other. And that can be quite significant. So this is just showing in the top panels number of mergers above some redshifts, and you can see that we can have up to an order of magnitude difference depending which seeding model we assume. And we can actually quantify that in terms of observables. So we can construct something that's called the chirp mass. That's essentially combinations of masses of the two black holes that merge, that has some redshift dependency into it. And the LISA sensitivity is plotted here. And essentially with different seeding models, we can see that LISA will be able to distinguish these models as a function of cosmic time, which is really good news. Obviously, the degeneracies with the accretion and feedback and so on that we additionally have to work on. So finally, I want to, in this kind of topic, to mention the last thing, and that's what is becoming more and more interesting recently, the multi-messenger astronomy. So when we have a black hole merger, how the, for example, optical counterpart looks like, can we connect the two? Can we learn something about this? And Colin is currently writing a paper about this, and he has been looking through both Illustris and Illustris TNG simulations and looking when the black holes merge, and then tracking the host galaxies both backwards and forwards in time and looking at their morphologies. So here are some mock observational pictures. So this is an example of a dry merger. So the black hole merger happens right at the second row, at the first panel, when you can see these two double nuclei. This is how the galaxy looks before a merger. So it's an elliptical galaxy with a bar. And then after the merger, you can see all these nice shells that are telltale signs of a merger. And this is another example in a spiral galaxy. So you see a very gas-rich system, then a merger again happens in the second row, and then you see the tidal tails and the perturbation in the gas that are again indicative of a merger. But you can quantify that statistically through the M20 and Gini parameters, and essentially that's what Colin has done. And he has found that provided that you have sufficiently major merger between the two black holes and that the black holes are massive enough, there is a morphological signature that could be detected. So these are essentially these red points shown here on the bottom, and that is very interesting. And usually these type of objects lie, of course, at the massive end of the scaling relation. So they will more be in the pulsar timing array window rather than the LISA window. So now moving on to the accretion business. So this was all about seeding is done. Some years ago, a former PhD student of mine, Mike Curtis, has developed a new algorithm in a code that we use, which is called the repo, to try to bridge some of these dynamical range in spatial and mass scales that we don't have in the vicinity of supermassive black holes. So I won't go into too much detail. I just kind of schematically, visually show you how this works. So you have a simulated galaxy, and then on the fly, while the simulation is running, you try to crank up the resolution in the center further and further, and you have some parameters until you can do that. You can, for example, crank up the resolution to resolve the Bondi radius, or you can be even more ambitious and try to go all the way to the outer edge of the accretion disk. Which I'll show you towards the end of the talk. But then what is interesting is once you have this much higher resolution, so we can now increase the mass resolution in vicinity of supermassive black holes by 8 or 9 orders of magnitude, you can ask, even if you do a simple type of physics, like in terms of feedback, a thermal dump, will the results change just by changing the resolution of the simulations? And the answer is yes, and also significantly. So if you have a typical resolution without this special refinement that we do, this is shown in the top panel, and if you just thermally dump a lot of energy around supermassive black hole in the core of a galaxy, you generate this massive blowout, and you have a hot, essentially energy-driven shell that drives out and obliterates the galaxy, and you morphologically transform it. If you have much higher resolution and you dump exactly the same amount of energy, given that you, with the resolution, essentially what you are following is very dense pressurized gas, much closer to the injection region, what happens that this gas can now finally resist, essentially the cold disk can resist the outflow, and it can collimate it, a little bit like the Lavel's nozzle. So instead of the spherical blast, you're actually generating bipolar outflows just by hydro, so just by the pressure support of the gas that you're finally resolving. So then you can ask, in a more realistic scenario, does this still happen? And the answer is yes. So we had a paper some years ago where we have simulated what we call the zoom-in simulation of a high redshift quasar. So it's a very massive object of order of 10 to the 9 solar masses, surrounded by a which is rotationally supported, as you can see here from the other inset plot, and you have a massive hot outflow, which again is collimated just by the disk itself, and it's bipolar, and it's leaving the disk. So it's actually not morphologically transforming the disk. And that opens a really important question, is whether we have understood essentially the Hubble sequence. So how morphological uh, evolution of galaxies happen, how do we go from this cold, dense, rotationally supported disk to this dispersion dominated system, and just is this really just a supermassive black hole feedback alone or not? So let me move on now to a more recent and maybe more controversial topic, but still highly exciting, about AGN feedback in dwarf galaxies. So it has been more or less a standard law for a number of years now, maybe 10, 15 or more, that to get the galaxy properties right in this cosmological simulation, what you need is a very strong stellar feedback at the low mass end to push the stellar masses down compared to the halo masses in agreement with observations, and you need a very strong feedback from the AGN at the massive end to do the same type of game. And that has been driven mostly by the fact that you can more or less successfully reproduce a bunch of observations in that way. However, more recently, there has been a number actually of observational evidences that there are some dwarf galaxies that host AGN, and then it is a small population at the moment, but there have been very exciting both works from manga and optical and X-rays and radio that have shown that actually in some cases these AGN in dwarfs are actually shining at a luminosity comparable to the Eddington luminosity, which in such small systems should do some damage. So recently my student, Sophie Kudmani, has looked into this using one of our past cosmological simulations.
Deborah, 5 minutes more. Sorry, 5 minutes more.
I have to go even faster. Okay, I'll try. So she has looked into our cosmological simulation box, which we call Fable model, and she has tried to actually look at all dwarf galaxies and look in detail whether they have any signatures of AGN outflows or such high luminosities as these recent exciting observations seem to indicate. And so what she has found is that if you look at the black holes that for a given, let's say, gas mass or stellar mass are overmassive compared to the scaling relation, you actually find that they can, just focusing on this highlighted panel, that they can drive much hotter and much faster outflows from the dwarf galaxies, which is very interesting. And also they can do some damage in quenching at higher redshifts. So I skipped the manga stuff. If you're interested, I can talk about this later, but I just want to highlight that you can make now predictions for the AGN fraction in dwarfs at high redshifts that the future missions such as Lynx and Athena will be actually able to observe. And the fraction of dwarfs, what we find here, modulo obviously seeding uncertainties, that should ramp up rather rapidly at high redshifts, which is very exciting because that can be then tested with observations. So let me now just tell you very quickly about another thing that's very close to my heart, and that is finally about trying to put jets in cosmological simulations. And that's thought to be one of the crucial ingredients of actually heating intercluster medium in galaxy clusters. So we have been working on this for a while. So the main driving force behind it is my former postdoc, Martin Byrne, that has developed a whole new technique I won't go into to simulate these jets in cosmological simulations, where again, a lot of refinement is needed, a lot of dynamic range to do this. And more recently, he has done it for the first time in a live cosmological galaxy cluster. So this is just showing you how the galaxy cluster looks like. This is a really large scale view at in a local redshift. This orange circle is the virial radius. And then you can see this tiny, tiny pixel here in the center, I hope. That's actually, if you zoom in into this region, that's where the jet lives. This is the high resolution jet that we inject into this galaxy cluster. And then you can zoom in, for example, in this dashed green rectangle, and then you can see all the resolution, sorry about this, that you can get in the jet lobe. So you can see all the beautiful streamlines here. So you can get a turbulence in the jet lobes, in the cocoon. You have the contact discontinuity at the edge of the bow shock and stuff like this that we can now resolve for the first time. So we had a little bit of a press release and trying to make the game to try to look, our simulations look like observations, which was fun. But more importantly, we try to actually identify which mechanism leads to energy transfer from the jets into the intercluster medium. And the story here is actually very simple. It's all to do about having essentially internal shocks in the jets that thermalize the jet material, so transfer kinetic energy into thermal energy within the jet lobes, and then this thermal energy can be communicated effectively to the intercluster medium due to the PDV heating and mixing. And that's what we found. So this is summarized in this paper. And more recently, we have submitted the next paper that just came out over summer, where we have now explored different jets in the same cluster with a different power. So these are all fixed power jets, but of different power. And what we have found here, so these are some mock X-ray and radio images of different power jets that you can essentially have a transition from something at the low powers that looks more an FR1 source to something that looks more like FR2 source with the hotspots. So in the very last bit, 1 minute of the talk, I just want to advertise a very recent work of my PhD student, Rosie Talbot, and she has tried to complete what we would say the feedback loop. So what is the idea here? So we have our special super Lagrangian refinement, where we track mass and angular momentum flow until we can resolve this in the simulation, and we try to tie in resolution to the outer accretion disk. Then we have a subgrid model for Shakura-Tsunayev disk, standard disk, which can have a tilt. And then we implement on top of that a Blandford-Zanaev jet that power and spin direction and torquing is all self-consistently coupled to the accretion disk physics itself. So it's very much drawn from analytic theory, and of course a lot of GRMHD simulations, because we have to assume something about the magnetic fields at the black hole horizon. So the exciting news here is now that we have jets that can have varying powers. So these are just some examples of jets that we have been shooting them in different environments, and we have been also shooting jets directly into the circumnuclear disk of the galaxy, generating this massive outflow. And now we can look at, for example, the spin torquing, and we can look at the spin up due to the accretion. We can look how the jet power varies across the time, and we can also see these intermittent inflows onto the black hole that is obviously modulated by the viscosity of the Shakura-Tsunayev disk. And this
1 minute, Deborah, please.
Yeah, I'm wrapping
so we have some time for questions. Thank you.
Yeah, I'm wrapping up. So essentially this paper will come up very soon, so there will be all details in it. So let me come to my last slide. And I would just say there is, yes, a lot of hard work in front of us, but I think the future is really bright, because recently we have been making a lot of progress in getting much better, more sophisticated subgrid models. And I think we can start to unravel some new physics of supermassive black holes in this type of simulations and try to tackle some so far unanswered questions. So thank you very much for your time and attention.
Thank you, Deborah. There's no time for applause, but I'm pretty sure you would receive a huge applause if we were in the room. So I open the floor for questions. I'm sorry for pushing you. So we have like 3 minutes for question. You can unmute yourself and ask a question or write in the chat.
Okay, can I have a question? Yes, I'm Michal Bilek, and I wanted to ask about the dwarfs with the AGNs.
Yes.
So is there any difference in the baryon fraction of the dwarfs with the AGNs and those that don't have AGN?
Yes, there is a massive difference in the gas fraction. So you really, for these black holes that are overmassive for their host, you can have significant drop in the gas fraction or in the dwarfs.
And what about the baryon fraction? I don't mean only gas fraction, but
yes. So the stellar fraction, that's a bit more tricky. So I couldn't enter into any details. So we have taken the simulations on purpose, where on the low mass end, like in all standard simulations, supernova feedback is regulating the stellar masses in dwarfs. But notwithstanding that, so majority of stellar mass regulation, so bringing down stellar fraction, is driven by supernova feedback. But notwithstanding that, at high redshifts, where the black holes accrete a lot because of downsizing, and that happens, essentially we find that there is reduction in the stellar fractions as well from the AGN in dwarfs. But if we would have a different model for supernova feedback, it could happen that this is actually even a bigger effect. And in fact, this is what Sophie has been working on now, trying to explore different supernova feedbacks that are not so aggressive and see what the AGN are doing in dwarfs. I think it's an open question.
Okay, so now you spoke about the simulations, and what about the observed ones?
Yes, so in the observed ones, I think the best so-called, I would say probably the best evidence so far comes from manga, because they have nicely kinematically resolved. I just couldn't talk about this. I ran out of time, unfortunately. So this is shown a little bit here. So these are our mock manga images. And what people talk about here is these kinematic offsets between the stars and ionized gas. And there was a really nice paper by Penny et al. Using the manga data, and they found this significant kinematic offset. So it means that there is you could interpret it. It's not kind of 100%, but you could interpret it that there is a massive outflows that is driven by AGN, and that is kinematically offsetting ionized gas. And we have tried to quantify if manga data can be interpreted in that way. And in many cases, this is indeed the case due to the AGN feedback.
Okay, thanks.
Thank you, Michael. Do we have some more questions, please? So you can just simply unmute yourself and ask a question. So if anyone else? If not, I would like to thank Deborah once again for this amazing review and the amazing results you are having. We are going to look for the bright future and looking forward to this super good, super resolution simulation. That's going to be very exciting. So thank you, Deborah.
Thanks.
And we move forward now to the next speaker. This is Professor Luka Popovic from the Astronomical Observatory in Belgrade. And Luka, if you can please share your screen. I saw it for a minute. Okay, thank you very much. The floor is yours. I'm going to warn you 5 minutes before, and I'm going to leave 3 minutes for questions. Thank you very much.
Okay, thank you, Dragana. And also, I would like to thank to organizers for inviting me to give some recent results about polarization in active galactic nuclei. So this work is a common work with Professor Viktor Afanasyev and Elena Shablova-Binskaya from Special Astrophysical Observatory in Russia. So let us repeat something that also we heard this morning. Dragana said about the AGNs and the structure of AGNs that you can see here. We have very complex structure inside. It means to have a supermassive black hole and also accretion disk, and we can expect some outflows. In any case, we can expect some dust around the supermassive black hole. So it depends from the 2 or 3 things that we can see lines in optical port, lines in the spectrum of an AGN. The lines can be very broad, around several thousand kilometers per second, and can be also narrow line. So in any case, it depends from the type of the galaxy to have narrow line galaxies or broad line galaxies. So we can call it type 1 or type 2 AGNs. What is difference? In principle, we have several things that they are influenced to see type 1 or type 2 galaxies. First of all, it is dust. and also rate of accretion. It means that they are connected, because if we have more dust, probably we can expect more rate of accretion. And also dust distribution. It means that we can see broad lines if we're looking like this in the heart of the AGN. And we can see only narrow lines because they are forming somewhere here if you're looking like in this direction. So it means that orientation is very important. In principle, when we observe polarization in AGN, we have a little bit different situation, similar but different, and also we have some difficulties in the polarized light. First of all, we can expect that we have sources of polarization. They are coming from the accretion disk, from radiative transfer of accretion disk, but also in broad lines, we cannot expect polarization in broad line region because there are clouds, you know. So then we can expect that polarization in broad lines is coming from the scattering that can be on the dust and electrons in outer part of the broad line region, or dust that is in the inner part of the torus that is shown here. Also, we can expect that we have some scattering on the outflowing material, and then we can expect also that polarization is different in different types of AGNs. So it is interesting to see that in principle, we show it in one preceding papers where we measured angle of polarization of Seyfert 1 or Seyfert 2 galaxies, and we found that they are quite different because Seyfert 2 galaxies have some higher polarization angle. It means that we are looking in this direction, and Seyfert 1 galaxies, they have smaller polarization angle that we are looking in this direction. So in the case of polarization, as it was noted in Smith et al. In 2004, orientation is very important. Polarization in AGNs is very important because, first of all, we learned from polarization. It was the paper earlier, Antonocci and Miller in 1985, that also the AGNs with narrow lines are hidden, have hidden broad lines that can be seen in polarization. So after that, we start to develop several models. First of all, Smith, and after that, Guzman and Gaskell. And also, we, with George, developed some models of polarization in AGNs. What we can have from polarized light in AGNs. First of all, we can measure the masses of supermassive black holes. That is very important. We gave a method I will mention later on. And also it's very important because a broadline region, as Dragana mentioned in the morning talk, cannot be resolved in many galaxies. We have some observation in gravity, but the structure of a broadline region or region that emits broad lines is still unknown. Then we can measure the radius of inner part of the torus, or very important, the dust forming region. I point out once again that dust and dust distribution beside accretion in the center is very important for an AGN. And then we try to answer also what is the nature of polarization in gravitational lensing. So type 1 AGNs, we expect to have some so-called equatorial scattering. What it means? It means the scattering for broad lines will be on the region that is equatorial to the flattened broad line region. And then we can expect two effects in broad lines. First effect is that we can see broader lines that usual in non-polarized light. And also we can expect to see some specific shape of polarization angle. As you can see here, we call it S-shaped. So what is interesting in this polarization angle is if we measure, if we know this distance of scattering region or dust forming region, and we measure the velocity across the lines, we can connect velocities with radius from the black hole, and radius of the cloud from the black hole we can connect with radius of scattering region. It means that this connection can be used to measure the black hole masses. In principle, we did it, and what it means? You can see here different velocities. Then we have one shape of polarization angle. This is the line profile. And after that, we can use simply velocity as function of logarithm of polarization angle. And we can expect one line that will tell us two things. First of all, we will see if there is Keplerian motion, that the inclination should be minus 0.5. And second, from this, we can measure the so-called parameter B here, that inside has the mass of black hole. So we measured it and showed it in a paper in 2015. And it was interesting that we found that we have some points that they are not fitting very well the Keplerian disk that we expect in the case of smaller velocity. And then we obtained very good agreement, our measurements of black hole masses with reverberation. So it was a reason to model this situation, and it was in the paper in a couple of papers of Savic et al., where we showed this model that we have inside broadline region, Keplerian-like, and we have a scattering region here. So you can see here torus, and here is broadline region. And then we modeled the shape of polarization angle, and also modeled the line and polarized line. So it is some case with pure Keplerian motion, but we also consider, as Deborah said, that we can expect some outflows very close to the black hole, supermassive black holes, and we measured also modeled also some outflows that they are somewhere about 2000 kilometers per second, and still we can recognize the shape, and still we can measure the masses of black holes. Also, we compare our observations with theory, and as you can see, the theory is in good agreement with observations. So we recently we tried to use different geometries, and also use disk-like outflow and spherical geometries. And you can see here the pictures of the torus and the broadline region in the blue wing line center and red wing. As you can see, using polarization, we can see different images of the broadline region, but also different images of torus in different line parts. It's very important because we can use polarization in the line, in broad lines, to find some characteristics of broad line region. And we did it for 30 type 1 AGNs. We observed it with the 6-meter telescope using Scorpio. Spectral coverage was between 4,000 and 8,000 angstroms. We have spectral resolutions of about 5 to 40 angstroms, and accuracy of measured polarization was between 0.1 and 0.3%. That is high precision of polarization. On this plot, you can see the results of our observations. So first plot is the line, age alpha line. Second and third plot are Stokes parameters. After that, you can see polarization, the rate of polarization and polarization angle. And as you can see, in all of this polarization angle, we can see some specific S profile that is used to measure the masses of black holes. It was amazing that we check it with the sigma m relation. That is very good. And what we found very, very nice agreement between sigma. So it means that measurements of black hole mass with this method can give very, very good results for the masses of black holes. Also, we use this method for these 30 galaxies to estimate the inclination of broad line region. We expect to have inclination, and we use the observations in reverberation of these 30 galaxies to estimate so-called, this part here, virial product that has, you can see here, radius, velocity, and gravitational constant. And this F factor, so-called, depends from the inclination. Of course, the factor depends mostly from inclination, but can depend also from different geometries. Some example, if we assume Keplerian-like geometry, we can find a relation between F factor and inclination. And then we use our measured black hole masses, because they do not depend from the inclination, and then estimate F factor, and therefore after that they estimate also inclination. What we found also that inclination in type 1 galaxies is in the verge somewhere about 30 degrees. That is expected if you remember the angle of view. Then we expect that the type 1 galaxies with broad line have somewhere between 30 to 40 degrees inclination. Also, we try to do something more. It is not so easy. If you have this polarization angle, it means that polarization angle is here, and here is the line profile. So we can expect that we have some maximum in the polarization angle that depends from the angle of view of scattering region from this. So you can measure dimension of broad line region, but not photometrical dimension as it is case in the reverberation, but real dimension of broad line region. So we estimate these dimensions, and what we found that we have somewhere broad line dimension estimated from reverberation with maximal dimension as 1/3 of maximal dimension. Next that we found is that scattering region is somewhere about twice of the dimension of broadline region. That is fitting very well theory, photoionization theories that we expect to have something like this. So we are going to investigate high redshifted quasars, and then taking into account that regions of emission of H alpha, H beta, and magnesium are different. So then we modeled it, and it is published recently in monthly notices. But also we observed one quasar, SBS 4019 plus 538, that has redshift 1.862. You can see observations of magnesium. You can see this is line. This is Stokes parameters that we obtained. And also polarized light, you can see here. We have something that is telling us about might be some outflow, but also we can see S-shaped profile here that can be used to measure black hole masses. We found that the black hole mass is somewhere order of 10 to 9 solar masses. That means that is very massive quasar. Using this method, the problem is to find the dimension of inner dimension of torus, or better to say, to find the region where we have dust forming or dust forming region. So to find this, we have to measure this radius, to use the method for measuring of black hole masses, and then reverberation can help. And Dragana told as an introduction about reverberation. I will not repeat it. So a different problem can be solved. Also, we have proposed a project to our fund of science, Extra Universe. So this is something that we can use to measure the inner radius of the torus.
Luca, 5 minutes, please.
Sorry?
5 minutes. Just...
Okay. And then it was measured from several papers from Kishimoto, and we can find, but the method is time consuming, and also very, how to say, we have few objects that we measure the outer region. So we have to think about use polarization to measure this region. So simply we use the same philosophy, that is reverberation of measuring a broad line region using different scales in the polarization. And then what we propose, because we have from the central part, the ionization is changing, and then we expect to have dust in one region here concerning our investigation in polarization. And then we propose to measure different times. It means if we have continuum emission, this is time t1. After that, the broad line will react on the continuum emission, it is t2. And polarized line, that is mostly affected by scattering region in the inner part of the torus, here somewhere, will have t3. So we propose to have reverberation mapping, and we did it for Mercurian 6. You can see here light curves in the continuum line and the polarized line, and then you can find here the cross correlation function that there are several days for the time delay between continuum and the broadline region, and somewhere about 100 days delay between continuum and polarized lines. That is in very good agreement with reverberation in infrared. And also we try using this also project to start with new program of reverberation in polarization, as Dragana said, and also to include inside 2-meter Asiago telescope, 2-meter Rosen, and also our telescope at Mountain Vidojevica. It is something that we would like to do, and I very shortly would like to say about polarization in the lens quasar. So we have a program to find the nature of polarization in lens quasars. So first of all, we published also recently one known lens quasar 1004, SDSS 1004 plus 4112. What is problem? It is that only in the component A we see this is C4 line. We see some bump in only component A. You can see here, but in component B, C, and D, you can see here the images of the quasar. We cannot see this bump. So it is a question: what is the nature of this bump? So we observed in the spectral part. You can see our observations, and also observe polarization and model polarized light, taking that we have polarization in the torus. You can see here Stokes parameters, and also you can see here polarization and polarized angle. So we obtained following. First of all, this is on these plots or Stokes parameters, U and Q. And you can see this is the picture of the object, and A component is present on this picture. B component is present on this. C component, you can see here, is present on this plot, and D component on this plot here. So this is polarization. When you measure polarization parameters, what you have? You have that, first of all, very similar polarization parameters are at A and B, and also C and D here. But only we have variability in polarization in component D. So we conclude that we have microlensing influence on component D, because macro lensing cannot explain this variability. But also we can expect the influence of macro lensing, because, some example, if you have face on torus that has a larger dimension, torus will be projected on the lens like this, and we can expect different polarization parameters in the different images. So I am finishing with lecture and leave you with conclusions. So you can ask me if you find something interesting. Thank you for your attention.
Thank you, Luca. Thank you very much. And I open the floor for questions. I remind the participants, the attendees, just to unmute themselves and ask question or write a question in the chat.
No questions?
Could I ask question?
Yes, please, Alexander.
Hi, Luca. I would like to ask a question about polarization in magnetic field. You know, Sometimes synchrotron emission is very important for some AGN, and also in previous talks it was mentioned. But if you have synchrotron emission and you, polarization is very important signature for synchrotron emission. In this case, there is, in principle, there is opportunity to evaluate somehow a magnetic field in AGN. You analyzing polarization in this object, at least with toy models. Thank you.
Yes, thank you. Thank you very much. Very good question. But Sasha, here I am talking first of all about polarization in the line profile. That is coming from broad line region. And we cannot expect that we have some big influence of magnetic field in the line, in the polarization in the line. In continuum is different, you are right. In continuum, we can expect that even we have contribution from the accretion disk. If I remember, Chandrasekhar calculated that it can be until 10%, you know. And then we can have polarization in the continuum that is coming from cyclotron, that it is usual in radio loud objects. But in line profile, we cannot expect to have a big influence of this magnetic field, you know. Might be I'm not right, but I think because line is formed from the clouds that they are moving, and we cannot expect a radiative transfer in broad line region.
Okay, thank you, Luca. Thank you, Alexander. If there are no more questions, I would like to move forward. Thank you once again for the nice presentation. And we move forward to the next speaker, Mirjana Povic. She's already ready. I want to thank Mirjana for joining us here. And she is one of the key persons for the development of astronomy in Africa, and especially nowadays in Ethiopia, as she's part of the Ethiopian Space Science and Technology Institute. And she will tell us today about the Green Valley of Galaxies. Thank you, Mirjana. I do not hear you.
Mirjana, can you unmute yourself, please? Just unmute yourself. You are unmuted now. You are welcome, Mirjana.
Can you hear me now?
Yes, perfectly.
Okay, perfect. Sorry for that. So hello, everybody from Ethiopia, and thank you, Dragana, for introduction. I would also like to give my thanks to all organizers for making this meeting possible for all of us. Last year, when I got the invitation from Jelena and Angelka, I was really very much excited, and I was looking forward to this meeting to see all of you. So now, due to the COVID, we are able to only see each other in this way, but it's still better than nothing. So thank you very much once again. I will actually in Ethiopia in the past 4 years, we are really under the good progress of the development of the different studies that we are doing regarding the AGN. And then for this talk, I chose to speak more about the Green Valley galaxies and then the role that AGN might have in galaxy evolution. So I will first just briefly introduce what the Green Valley galaxies are. So basically in optical, mainly in optical studies that have been done previously using the large data sets, it's been seen that the distribution of galaxies is B-model when we compare different properties such as colors, stellar mass, star formation rate, or specific star formation rate. And here you can see the example using Sloan data from 2014, and then including the information about morphology on the two plots on the left, where you can clearly see when you compare the colors and then the stellar mass, the B-model distribution, and that the majority of galaxies are distributed either in the red sequence So this part where we have the redder colors and a bit higher stellar masses, and where in the majority we find early type galaxies. And then we have another area with a large fraction of galaxies, the blue cloud, where mainly we are finding late type galaxies. So basically the region between these two, where we are having lower fraction of galaxies, is what we call the green valley. And it's been suggested that this area is actually area that where the transition of galaxies is happening. So basically very important for studying the galaxy evolution and how the galaxies are moving from the blue cloud or late type to the early type galaxies or red sequence. So this has been seen on the lower redshift using large data samples like SLOAN or Gamma, but also at the larger redshift. So this is the example in Alhambra survey, where we also did the morphological classification of galaxies of the large sample of sources, and where we can also see that this beam modality between the early type galaxies that you can see here in red and the late type galaxies is maintained. So beside using the Green Valley as an important area to really understand in optical the galaxy evolution, it's been also suggested to be used for understanding better the quenching of the star formation. So this is the list of a bit selection criteria that we are currently having for selecting Green Valley galaxies. So a lot of challenge has been found in this aspect, and the different criteria have been used. So most of the works use the color criteria, either the near ultraviolet colors or just optical colors, and then the mix of the colors with the stellar mass or the absolute magnitude. Then also in some works, the star formation rate versus the stellar mass has been used, or the specific star formation rate, or just the combination between the 4 parameters that I mentioned. And recently also it's been proposed that DN4000 index can also be used for selecting Green Valley galaxies. In any case, we don't really have any precise criteria because whatever criteria that you use, finally we are depending on either visual determination of the green values or using a certain kind of fitting, and then simply selecting the area between the 2B model, between the two fractions or two areas where we have larger fractions of galaxies to be the green value. So that brings a lot of difficulties in interpretation of results. And in this work with Beatrice during her master, and now she's starting her PhD, we put a bit of efforts to understand better different criteria that have been used to select, to select and then analyze the green valley, and then understand better what kind of galaxies we are really selecting, and if that can affect our final results. So with Beatrice, we selected 6 criteria that have been the most used in the previous studies, and using both near ultraviolet data from GALEX and then the optical data from SLOAN. And we did find that actually we are selecting different galaxies in terms of the different properties such as stellar mass, star formation rate, also morphologies or spectroscopic types. And we found that the biggest differences are actually existing when we use the color criteria to select Green Valley galaxies, and that actually the diagrams such as star formation rate versus stellar mass or the specific star formation rate are much more stable in terms of selecting the Green Valley, even if you are having the optical or near ultraviolet data. But then, of course, using just photometric data and colors is much easier because of the availability of the data. Regarding the properties of the Green Valley galaxies, I will just summarize some of the recent results. So in most of the results, it's been seen that these galaxies have actually intermediate properties between those of the blue cloud and red sequence. This is, here are some of the examples from a recent work from Philips using gamma data, where we can see that, for example, when we are studying the stellar populations or the average stellar ages. The green belly galaxies have really ages that are between the blue cloud and then the red sequence, although closer to the red sequence galaxies than the spiral ones. And here you can also see, if you compare now the e-falling times or time scales that are basically related with the star formation histories of galaxies with the stellar mass, that again, the properties of green belly galaxies or the distribution is between the blue cloud and the red sequence. We can see that for the blue cloud galaxies, actually the time scales are quite high and not so much dependent on the stellar mass. However, for the green belly galaxies and then the red sequence galaxies, we find a much stronger dependence and faster time scales in terms of the quenching. This is another recent work where the properties of green belly galaxies, actually the fraction of green belly galaxies has been studied in terms of the environment. And it's been seen in comparison with field group cluster galaxies that there is no much difference in terms of the fractions. So independently on the environment, the fraction of green belly galaxies that in this work was found is below or around 20%. And then if you compare, if you take into account simply the total population of green belly galaxies, it's been found that they are the higher fraction is present in field galaxies. But then if you want to see really the effect of the environment, and then you normalize the fraction of green belly galaxies with the fraction or the number of non-quiescent galaxies, it's been seen that actually the number of green belly galaxies is higher in groups and clusters, and also that it's dependent on the mass. As it is, as the mass is increasing, the fraction is increasing as well, and slightly dependent on the redshift. Suggesting that actually the environment does affect the fraction of green belly galaxies. Another, in another recent study, people also try to see the distribution and the correlation between different parameters, such as, again, the average age, the time scale, or the metallicity and extinction in terms of the velocity dispersion, finding the linear correlation in all cases, and then comparing between two different selection criteria without really finding big changes, but the authors reported a bit better correlations when the DN 4000 index is used. In this work recently, we also found that important fraction of about 30% of green belly galaxies are related also with the galaxies that are inside-out assembled candidates. So basically, in this work with Dejeune is now, it was during his master, and he's now doing his PhD in Chile. So with Dejeune, we try to understand better what are actually the properties of inside-out assembled galaxies. So we used the previous results from the Khalifa survey, where my colleagues used IFUS data, and saw that there is a certain range of stellar mass that for which the galaxies are showing highest growth rate, or basically shorter assemble times within the inner regions, so within the 50% of the half-light radius. So we basically used SLOAN to select these sort of galaxies, and then we studied different properties, and we saw that in about 80% of the galaxies we find the signs of AGN, so either the composite galaxies or just AGN. That the majority of these galaxies are still with spiral morphologies, and that either they are below the main sequence of star formation, or, as I said, within the green belly and then the red sequence. And basically here we can see just the plot where we have the distribution of our sources in terms of the spectroscopic type and morphology, and then their location in terms of the infrared transition zone. And we basically found that high fraction of these inside-out assembled galaxy candidates are actually in the process of quenching, that they do have, that those that have AGN have lower star formation rates, showing the signs of that maybe the AGN can be related with the quenching of the star formation. However, having still the spiral morphology, we suggest that the central star formation, although being suppressed might happen before the morphological transformation actually occurs. So we published this recently. And in this slide, I will just briefly go through the suggested timescales. So basically, as I already mentioned, these galaxies have been suggested to be really important in terms of understanding better the star formation quenching and the transition between the blue cloud and red sequence. And in previous studies, there have been really different studies done using different methods, and different timescales have been suggested. So basically, from the short timescales below 1 gigayears up to the non-single transitions between 1 to 2 gigayears for intermediate transitions, and then even the slow quenching has been suggested above 2 gigayears, or in the most recent studies, like in Philips, they go even up to 7 or 8 gigayears that the transition can take place. In this work, again from 2014, from Chavinsky, they studied the timescales again in relation to the morphology, and they've seen that actually the early type galaxies within the Green Valley are quenching much faster, even below the 250 megayears, and then for the late type galaxies, that the quenching is going much slower. This is the summary of different mechanisms that have been suggested in different works responsible for quenching of star formation, including the AGN negative feedback, and then minor major mergers, the effect of the environment, the supernova winds, the secular evolution as well. And recently also it's been seen that in this work from Nogueira Cavalcante from 2019, using J+ data, that also the structure can be related, of the galaxy can be related with the quenching, and they studied in particular the bar galaxies, and so that if the galaxy has bar in comparison with a fraction of spiral galaxies in general, that the quenching is even slower. So the second part of the study, I will now focus more on what the AGN how the AGN can play the role in star formation quenching. And basically, in 2012, we analyzed the properties of X-ray detected AGN, and then in terms of their morphology, and then in terms of other properties such as their colors and stellar mass, luminosities, and so on. And we found that the majority of our X-ray detected AGN were actually located in the Green Valley. That was in the line with different previous studies. And in this work, we saw that actually independently of the morphology, so for both late and early type galaxies, we found that they are located in the Green Valley. This is in line with more recent studies that have been done in optical using large data sets like the SLAN data in the recent work of Leslie, where now using not X-ray detection of AGN, but optical detection through the emission lines, it's been seen that once you have the AGN, the galaxies will start moving from being on the main sequence of star formation, like in the case of star-forming galaxies here in blue, they will start moving below the main sequence of the star formation, like in the case of Seyfert-2 galaxies, or even below in terms of the liner galaxies. So basically, in both of the studies, it's been suggested that AGN could affect then the star formation in galaxies, and it's been suggested that the negative AGN feedback could be one of the causes of the star formation quenching. So having this in mind, we did several works with Antoine during his master and now during his PhD work. PhD thesis, we went a bit deeper into analyzing the properties of AGN and non-AGN galaxies inside the Green Valley, with the aim to understand better really what the role AGN could have in galaxy, in morphological transformation of galaxies, and then galaxy evolution as well. So We used the data in the Cosmos survey, so we went a bit to the higher redshift, up to the redshift 1.2, and we selected, used the X-ray data again to select the AGN, and then we selected also the non-AGN galaxies in the Green Valley using the color criteria. And the main aim was really to understand, to study different properties such as the star formation rates, morphologies, the stellar population, and then also recently we are studying, analyzing the profiles of the oxygen-free emission line. So in the first work that we did with Antoine, we wanted to understand better what to compare the star formation rates and to understand better the properties of the star formation in AGN and AGN galaxies. So we used the far infrared data with Herschel and then mid infrared data with Spitzer to measure the star formation rates through the spectral energy distribution fittings. And we did that separately for AGN and non-AGN, so using different templates. So in case of the AGN, due to the AGN contribution, we used the different templates in order to measure what the AGN contribution is. And then in both cases, we measured star formation rates through the infrared luminosity, but in case of AGN, we used the corrected infrared luminosity after removing the AGN contribution. So this is the diagram that you can see where we compare the star formation rate with the stellar mass, and we have the straight solid line is the main sequence of star formation. And we can see that actually here, this is, as I said, the final star formation rates measured with corrected infrared luminosities for AGN. And we can see that basically both AGN and AGN galaxies are lying on the main sequence of star formation. So we don't find the same results as in optical, that AGN are located below the main sequence of star formation. And now if we compare the star formation rate, we actually found higher star formation rate in these AGN galaxies. This actually has been seen also when we compare active, non-active galaxies within the same mass range, suggesting that for these AGN, that not only are detected in optical, but that are strong emitters in far infrared, we don't see the same results as in optical studies. We actually suggest that if there is any influence of AGN on the star forming properties of the host galaxies, then we rather see the enhanced star formation rates, and rather the positive feedback, AGN feedback taking place than the negative one. This could be, I mean, the higher star formation rates could be related not only with the AGN feedback, they could be related with other properties such as environments or the morphologies. So in another paper that we published last year, we studied the morphological properties, so going through the visual classification using HST data, but also going through the inspection of different morphological parameters, again, for both AGN and AGN samples. And what we found was that we do have certain difference between the morphologies. So we did find a larger fraction of AGN being in peculiar galaxies with clear signs of interactions and mergers, suggesting that at least in 40% mergers interactions could contribute to higher star formation rates. And then we found a bit higher fraction of spiral galaxies in non-AGN galaxies. We also obtained that different morphologies can be on the main sequence of the star formation. But when we again went into the comparison of the star formation rates, taking into account the morphology, independently on the morphology, we found again higher star formation rates within the same mass range for the AGN galaxies, suggesting again that morphology itself cannot again explain the higher star formation rates that we are observing in these sources, and coming back again to the possibilities that we might have here really good candidates for studying in more details the positive feedback. I didn't mention that the negative feedback in AGN has been studied quite a lot. But the positive feedback and the evidences of the positive feedback in terms of the observations, we don't have so much. So maybe we really have to go more to the far infrared data to really understand the positive AGN feedback as well. And currently we
Miro,
are...
5 minutes more. I'm sorry for interrupting. You have
Yes,
5 more minutes.
I'm finalizing. Thank you, Dragana. So currently we are also studying the stellar populations in the same sample of AGN and AGN galaxies. So we used for a smaller sample of data that we have the legacy spectra, and we went through the spectral energy distribution fitting, and we obtained that the majority of our AGN have either intermediate stellar populations or younger stellar populations in comparison with the non-AGN. And in order to understand better if really we can see any signs of outflows and possible AGN positive feedback, we applied for the SALT observations, and we were lucky to get the time. So we got for now the time for 4 sources where we are observing the oxygen-free line, and we are now trying to study the profiles of oxygen-free line that previously has been suggested to be the good one for studying the outflows. And we currently obtained the data for the 20 sources that are under analysis as well. With this work, we saw that it is really important that we shift a bit to the multi-wavelength studies, not only to the optical studies in to really understand not only the properties of Green Valley galaxies, but also the role of AGN. And in this work that recently was published as well, it's also confirming that a little bit where people using a gamma survey, gamma data, you can see here on the left, again, B-model distribution when only the optical data are used. And then when you go to the sub-millimeter using H-atlas, it's been seen that actually the larger fraction of sub-millimeter galaxies is exactly located where the Green Valley is. So basically in this work, people suggested that the lack of the sources that we are having in the Green Valley in optical is not really the sign that we are missing the sources, is just the difficulties that we are having for not detecting all the sample of galaxies in optical. And once again, moving to other, we really need to move and to combine the multi-wavelength studies in order to understand the full picture of galaxy evolution, and then the morphological transition and transformation of galaxies. So this is just, here are just some of the take-home messages. The last one is the one that I just mentioned. This also includes the role of that the AGN can have in star formation quenching, where we found different scenarios when we use the X-ray data, when we use the optical studies, where it looks that the AGN negative feedback is really taking role in star formation quenching. But then if we use the far infrared data, we see that maybe we are having good candidates for the positive AGN feedback, where they can also enhance star formation in the galaxies. And then also another point is that being careful with the sample selection is really important in order to interpret at the end our results, because depending on the criteria that we are using, we are actually selecting different galaxies. This is, I'm finalizing, this is just a list of other projects that we are having under the Extragalactic group in Ethiopia and also neighboring country, in collaboration with Rwanda, Uganda, Tanzania, and then also South Africa, that is a bit further, not in East Africa. And you can see that here are some of our PhD students and master students as well. And most of the study is focused on active galaxies, including the study of the AGN star formation in galaxy clusters in the PhD of Tseleke, in collaboration with the GLACE survey and my colleagues from Spain. Then we are putting a lot of efforts to study in more details the morphologies of AGN, but taking into account AGN contribution. And we are expecting 2 papers from Tilakun to come out recently. With Paula, that many of you know and work with, and then with Johnny from Spain, we are also with Chimeles working on dichotomy of radio quiet and radio loud quasars. And then there are several works focused on the morphological properties, like multi-wavelength morphological study of AGN, then variability of nearby quasars, and then with Asrate and Daudi from Tanzania, we are also working on alternative methods for measuring the accretion rates in galaxies and trying to understand better the difference and the diagrams, how we can separate those liners that are not AGN photoionized and then retired galaxies. And then in my free time, currently I'm working on that I don't have much actually, I'm working on also the study of the stellar populations of the ultra-hard X-ray AGN that are detected in the bus survey, and hopefully we will be able to come soon with the publications. So thank you very much for your attention.
Thank you, Mira, for a beautiful talk. It's really amazing what you're doing over there. So questions from the audience, please unmute yourself and ask a question, or raise your hand, or write in the chat.
Can I
Luca,
ask?
please.
Yeah. Nice talk, Mira. Thank you very much, and also very hard work. And I am interested in the estimating of the star forming rate in the AGNs. You said that you subtracted some contribution AGN in the infrared part. How there is a program to do it, or you have some method to do it? Because
yes, so basically for the AGN, what we did, let me try to see if I can go back. I think I have to share now again the screen. Okay, can you see? Okay, here. Yes, so basically what we did was, so we first measured the star formation rates for the non-AGN, just using the templates of Chari and Elbaz. And then in case of the AGN, so we used the 11 templates from this work from 2015. And in this work, the 11 templates that they have exactly, can you hear me? Sorry.
Yes, we can hear you,
yes,
Mira.
I can hear.
So in these 11 templates, in this work, they have quantified what the AGN contribution is. So basically, we did the spectral energy distribution, like in case of non-AGN, using exactly the consistent, in a consistent way, but using different templates. Then we got what is the so what is the template with which each of our galaxy was fitted? We were able to measure what the contribution of AGN is using, as I said, the results from the 2015 paper. And then basically in this paper also you have for each AGN contribution, what is basically the factor that has to be applied for correcting the infrared luminosity. So we applied that factor to obtain the corrected infrared luminosities, and then we just used the same formula for measuring the star formation rates from Kenninga that I put here that we used for non-AGN as well.
Thank you. It's clear.
You're welcome.
Any other question, please? If not, I would like to thank Mira and to really join her thoughts that I'm sorry that we could not meet in person, but next time hopefully we will all be together. So thank you very much, Mira. And we move now to the next speaker. Svayam, are you ready?
Yes. Thank you.
Okay.
Dragana.
So I'm just introducing our very dear friend and colleague. So I am Trupa Panda from the Center for Theoretical Physics from the Polish Academy of Science. And he's going to talk about some exciting work about the optical iron and near-infrared ionized calcium emission in active galaxies. The floor is yours. I'm going to give a 5-minute reminder.
Great. Thank you. Thank you, Dragana. Thank you very much to the organizer, first of all, to give me this opportunity to present this work. So together with Marie Lawley, this is like an ongoing project, and we are happy to present some of the initial accepted results that we have been doing for this particular year. So hello, everyone. As Dragana mentioned, my name is Swayam Trupta Panda. I'm supervised by Professor Božena Černý, and I work jointly at the Center for Theoretical Physics and at Copernicus Astronomical Center in Warsaw. So today I'm going to talk about this optical Fe2 and the near-infrared calcium-2 emission in active galaxies, which we kind of give a nickname, the CAFE project. And so before I go any further with this science, I would first like to take a brief moment and thank all of my collaborators, especially who are present here. Marie is already here. Because without them, this project wouldn't have been possible. And there are a lot of open channels for this project to keep on carrying further. So the current timeline for this project is already in stage 4. But today, I'm just going to focus mostly describing you the initial observational sample and the detailed photoionization modeling that we did to account and compare these two species. All right, so the motivation behind this task was basically just this phrase, to understand the physical conditions in the broadline region in active galaxies. As Dragana, as Professor Luca and others have already pointed out, it's so complex to understand the geometry and the emitting region of these broadline regions. And especially I have this cartoon set up just to give you a brief idea where we are in this kind of big puzzle scenario of understanding the broadline region. So essentially, this is comprised of these 4 components, if I may, alongside with other effective parameters which are not shown here, but potentially these are the 4 important parameters. So we have the radius luminosity connection, the density of the medium of the broadline region, the spectral energy distribution, or the ionizing continuum that heats the broadline region and effectively then producing these emission lines. And of course, the composition and the size of this broadline region, which Professor Luca also pointed out. Well, I should not be telling you more about reverberation mapping because it has already been told in much detail in the previous talks. But just to give you an idea why it is so important. So basically, this methodology incurs the light echo method. So we have the continuum sitting over here. That's the accretion disk thought as. And then one really tries to associate the mimicking of the continuum variability with respect to this large scale emitting line region. So by studying them cohesively, we could really test whether how big this emitting region is, and then essentially use this relation to derive the radius of the broadline region, which in principle is then extrapolated to be used in the virial relation to estimate the black hole masses. So this is that standard virial relation that Professor Luca also pointed out. So of course, there is the radius factor, this radius of the broadline region. We also have this effect of the velocity dispersion that we get from spectral analysis. So we effectively kind of estimate the, as a tracer, we use the full width half maximum of these broad lines. For example, here I'm showing this effect around the H beta line here. So that is also used quite robustly to estimate the standard radius luminosity and then estimate the black hole mass. But not to forget the effect of this F factor, the form factor, or this fudge factor, which takes into account all the information about the BLR inclination and kinematics. That is mostly all these elements that we still don't understand properly. Okay, so to go further in our previous works, we have already tried to establish and try to understand what really happens inside the broadline region, taking into account all the emission features that goes into it. So here I'm showing a simple cartoon from our earlier works where we have the supermassive black hole sitting on the left side of your screen. And then we have this sort of cutout diagram of the broadline region, a very simple cartoon here. So we have the highly ionized front sitting right in the first part, which is the fully ionized zone. And thereafter, we have these zones of emission for especially these 2 species that I'm showing, the H beta And later on, it was only at the far end of the BRR crowd that we see the Fe2 emission really peaking up. This is already confirmed from our photoionization modeling, where we see that over here, I'm showing this H beta and Fe2 emissivity profiles. So we are on the top here in the blue, it's showing the H beta profile. So we see that the peaking happens right around this corner, and the Fe2 really rises after this ionizing front of H beta is achieved. So, and this is really confirmed from the reverberation studies that have been carried by many researchers, especially by groups from Professor Wang's group, where they have also estimated that the Fe2 region is indeed a factor of 2 at least further away from the H beta emitting region. Well, moving on to the diaspora of the Fe2 emission, because that's the straightforward question. Why are we interested in studying this species in particular? So the fundamental driving motivation behind studying this line emission is because it goes into, without saying that, it understands the energy budget of the emitting gas, and is, by knowing the abundance of the species itself, can give us an idea of, as a function of the cosmic time, and thereby help us verify the cosmological parameters. The Fe2 emission is sort of very ubiquitously studied since like past 40 years right now. And we now kind of understand, we're starting to unravel the mechanisms that go into exciting this Fe2 mechanism. So we have the standard photoionization, continuum fluorescence, collisional excitation, self-fluorescence among the Fe2 transitions, and also the efflorescent excitation by Lyman alpha and Lyman beta. Well, to summarize the context of Fe2 emission, it's been really well studied and well put together in this paper by Werner et al. 99, where they say that this atom is far from equilibrium in most emission line objects, and this spectrum is really sensitive to detailed local fundamental conditions, such as the density, temperature, iron abundance of these emitting regions. Well, it needs no more introduction to say how typically difficult it is to recover such an emission, both by observation and modeling, because as you can see, I'm just showing a cutout of the theoretical UV and optical Fe2 spectra that has been calculated using photoionization code cloudy. And we are already accounting for 371 levels for this first ionized state of iron. So at the moment, the photoionization code cloudy just computes up to 11.6 electron volt for Fe2 and predicts intensities of over 68,000 lines in the optical UV itself. And a lot of study has been done, and actually it was initiated by the initial study of Burris and Green, where they really emphasized on the eigenvector 1 sequence and putting together the RFE quantity that Isidora talk, she mentioned about this as well. So the idea was very simple, was that they wanted to make a template of Fe2 spectrum by removing all other lines that were not Fe2. And this was done particularly for One'sWiki 1, which is a very well-known study source in our community. And after that, in the last 20 years, there have been a lot of progress, both by the theoretical studies, also taking into account the observational analysis. And what we really find out at the present moment is that the semi-empirical approach, which is like combining the theory and observations together, is one that really facilitates the understanding of this species. Well, I mentioned to you how complicated this species is. So basically, Fe2 is actually also sort of sometimes called a pseudo-continuum because of the plethora of lines that we see in this diagram here, which also consists of blended multiplets. So it becomes really a tough challenge to really dissociate all these different lines and transitions from each other. So many different groups have been working on this for, as I mentioned, like past 2 decades. And we can really see that there is still a lot of progress that needs to be done in order to understand the full capability of the species of pseudo-continuum of iron. Well, and also not to, it goes without saying that in previous studies, I think it was always considered the Fe as a contaminant in the quasar spectra. So the idea was just to be able to model that part of the Fe2 in order to emphasize more on the broad line lines such as H beta magnesium 2. But now we are pretty much sure, and it goes without saying that this is not just a contaminant, and it has been really ubiquitously used for studies like in the main sequence of quasar. So talking about main sequence of quasar, we have 2 fundamental diagrams, of course. One that comes from the Nature paper by Shen and Ho in 2014, where they presented this pizza main sequence picture, where we have on the y-axis the full width half maximum of the broad H beta line, And it is connected with this RFE content, which is the integrated intensity of the Fe2 lines in the optical regime, the blue part of the optical regime, and normalized with the H beta line. But there is a caveat in this, the picture is that it contains a diversity of quasars ranging from different luminosities and redshifts. So when we want to correlate it with something like the HR diagram, it was really essential in order to prune this sort of sample in terms of a redshift limited source. And this is what has been achieved in previous studies by Paola Mazziani and collaborators. And this is what we also presented in our past work last year, where we studied the main sequence of quasar, taking into account the, and really finding out that the Eddington ratio is the primary driver of this main sequence. But in order to do so, it also depends on the viewing angle, cloud composition, and the shape of the ionizing continuum. Talking about the shape of the ionizing continuum, it's really necessary to understand the diversity in terms of the source continuum, because really assuming a single source continuum could really lead to results that could may not be as realistic as we would think of. So here I'm showing these 4 examples of different sort of SEDs that we considered in the work, in our past work, where we really see that the part of, and this dotted line is actually at the 1 Rydberg mark. So we know that from past theoretical studies that the 1 Rydberg mark is the point where it's necessary for the species of hydrogen to be excited, and especially for the low ionization sources such as iron and calcium, it's also necessary to at least have sufficient amount of photons in this regime to excite intensities of these lines. Currently, I think in recent papers by Gary Ferlin et al., they have investigated this idea of the ionizing continuum to a further extent, taking into account the effect of the accretion rate and black hole mass that has on the shape of the SED. So these are 4 realistic SEDs that are coming from 4 different sources. And you could clearly see the differences that occurs because of the change of the ionizing continuum and how we can recover change in the number of ionizing photons when we consider a typical SED. Moving on, then we also have to consider the idea of the cloud compositions, because one doesn't really understand what goes inside the broadline region when we are talking about things like reverberation mapping. So this has been tested before by considering the effects of metallicity and cloud compositions, as well as the cloud column density, so how big the broadline region clouds can be. And this is something in work in progress, which I will sort of have a brief shout out towards the end of my talk. All right, so the stage is now set to introduce the main character in this study, which is the calcium triplet emission. This is calcium 2 emission, the first ionized state of calcium, which is the near infrared triplet, whose lines are at these 3 wavelengths. So here I'm showing a Grothian diagram, simplified Grothian diagram of this calcium plus emission, which is a much simpler atom with 3 multiplets from 5-level systems. So we can expect just 10 transitions out of this. And we are kind of interested in the one that is marked in this red box, these 3 transitions which are happening in the near infrared regime of the spectra.
5 minutes warning.
All right. So the calcium emission, yeah, thank you. So the calcium emission is in general a very, interesting property, which is marks with the extremely dense and almost neutral gas in the AGN. And studies which date back to 1989 have actually shown that the calcium can be an effective correlator with terms of BLR emission. And this is what we took further in testing in our models. So just to emphasize, this is that 3 lines in the near infrared. So we take on to an observational combination of theoretical modeling here. We have a sample of 58 sources now with optical and near infrared spectral info. And 5 out of 58 of these sources are actually observed multiple times. So could be interesting candidates for further changing look studies. And then we perform photoionization modeling with Cloudy, and we incorporate a 1-wiki-1 observational spectral energy distribution so as to not incur with the difficulties in modeling the spectra. And we apply a non-dusty BLR approach, which is a prescription given by the Nankova et al., where we take into account the UV luminosity of the source, the sublimation temperature, and the grain size distribution, effectively coupling together to give the idea of the sublimation radius. So here is the picture, which is actually accounting for the standard photoionization theory equation that relates the ionizing parameter, which is on the left side, to the photon flux, the net hydrogen ionizing photon flux over the density of the medium. So here I'm showing this cutout piece of the two models side by side, one for the calcium over H beta and the other for the RFE. And here we can really appreciate the region where we have both these emission which are correlated with one another. So now the question would be asked is whether we are really sure that Fe2 isn't in the BLR. And for that, we tested it against previous studies done by Alenka Negrete and collaborators. We took into account the reverberations mapped sources and put it on top of our grid models, which really show us that indeed the Fe2 is in the BLR in this context. As I mentioned already, these two sources are kind of correlated, and we see that in terms of the ionization and the density patterns for these two species. Coming together to the central picture of this source, so we did this modeling in terms of really understanding how the different physical conditions as well as the compositions really play a role in understanding this correlation between these two species. So we have the data from our 58 sources, and the models are accompanied on top of that to recreate this nearly 1:1 relation between these two species. And not to forget, we have done the testing over a wide range of metallicity and column density behavior accounted for the BLR models. So as to summarize, we have compiled an up-to-date catalog of 58 sources where we find this very interesting correlation between RCAT and RFE measurements. And we optimize this parameterization for photoionization modeling, and we lead to really finding the maximum emissivity for both these species in terms of ionization parameter and the broadline cloud density. And we test it further with metallicity and column density. So this paper is already accepted in APJ. So, and I put it here, the archive note, if you would like to take a look further. And just to summarize before I go, what's next in the studies? We would like to extend this correlation that we found in terms of physical observables. And this is something that you would see in the next talk by Mariloli, and where we probe deeper into a near infrared equivalent of eigenvector 1 schema and an improved radius luminosity relation using calcium emission strength. So I would leave here for the study, and just to mention briefly that there's another secondary paper that is coming on dealing with the anisotropic continuum emission from the accretion disk, and suggested by modeling as well as from observation. So I leave you here. Thank you.
Thank you, Svayam, for an amazing presentation. And I open the floor for the questions. So please unmute yourself or raise a hand, a virtual hand, of course. I don't see any raised hands. Any questions?
Yes, I have a question. Dragana Luka is here.
Hi, Professor Luka.
Yeah, nice talk. Thank you very much. And also, you mentioned the UV part of iron lines.
Yes.
So we also investigated the correlation between the UV iron lines and optical iron lines, and it means that they are not correlating very much, as we have different regions of formation of these two part of iron line. What your theory or models say about regional formation of the UV iron lines and the optical iron lines? Is the same region, or is it different?
All right. So with my naive understanding, what I have in mind is that both these lines are really like excited due to the Lyman alpha fluorescence. That is one of the major mechanisms that really excites these two sort of parts of the iron to emission. And what we see is actually that the first thing that really matters is the near infrared and the UV part of the iron. And the optical only is a much more lower level excitation mechanism that happens later. So there is some sort of a correlation between this. We found this with Professor Cherny and Marjana when we looked into the STSS set of all the quasars, which have both UV Fe and optical Fe2. But indeed, that is still not a confirmed relation that they behave 1-to-1. So there are some degeneracies around here, and it's well known that the number of transitions in the UV are far more than what we see in the optical regime as well. So, and of course, Yelena and your studies have already shown that how important the really picking these transition in different groups and multiplets is important in this terms, and how each of these transitions really are affected by different physical conditions.
Thank you.
Thank you.
Thank you, Svayam. We need to move forward.
Sure.
Thank you very much. And we now continue in the same manner. And I would like to invite Mariloli Martinez Aldama to speak about a new radius luminosity relation using the infrared calcium triplet. So Mariloli, the floor is yours.
Yes, I guess that you can hear me and also you can see my screen, right?
Yes, everything perfect.
Okay, so in advance, sorry if you can listen some noise, but I cannot control my neighbors since I am at home. Okay, so thank you very much for this opportunity. And I am Mariloli Martinez Aldama. I am a postdoc here in Warsaw, working in the Boschena Chernis group. And today I'm going to present some of the results that are joined with the previous talk. Okay, so I am not mentioned many things about reverberation mapping because it was very well explained in the morning. But the main idea is that if we can determine the time between the time has the emission lines response to the continuum variations, we can determine the size where the emission light is emitted. And it is important because we can estimate then the black hole mass. One of the most important results from the reverberation mapping is the radius luminosity relation. And it is basically that the size of the VLR is related with the luminosity. And the challenge is to try to estimate this exponent. So 10 years ago, the scatter along the relation was very small, as you can see here, and especially this kind of relation is particularly interesting for the single epoch spectra because we only need to know the luminosity and then we can estimate the size of the VLR and the black hole mass. However, now, with the inclusion of new samples, especially the SDSS reverberation mapping objects, and also a sample that include only high accretions objects that it's coming from the supermassive black hole project led by the Professor Jianming Wang, the inclusion of these objects increase the scatter in this relation. So nowadays it's quite risky to try to determine the black hole mass using this relation. So, however, especially with the superaccretor sources, we can see here apparently there is a trend. The colors indicates the accretion rate intensity. So the bluish colors are basically here, they show the larger departures. So this correlation suggests that the time delay is affected by the M dot. It was first suggested by the Pudou and also Professor Wang group. And this M dot is only a scale representation of the volumetric intensity. So basically is the volumetric radio, sorry, the Eddington radio. Okay, so if we consider that this departure from the radius luminosity is due to the Eddington radio or the accretion rate intensity, so we can determine this parameter delta R, that it's basically the difference between the time delay observed and the time delay estimated from the expected relation. And if we only try to correlate this parameter delta R and the Eddington radio or the this parameter M dot, we can see that there is a very clear relation. And only if we perform a fitting for this relation, we can correct our radius luminosity relation by this effect, and basically this is the result. So we applied this result, for example, for cosmology, because for cosmology it's very important to determine the luminosity distance with a high accuracy. Unfortunately, for cosmology, we are still far from the very high results that we need in that case. And also Natasha, in her work, she also tried to apply this correction to try to compare the black hole mass and from the black hole mass from stellar dispersion, but there are no very good agreement there. So there is some problems that we have to think. But there is other problem that since this parameter delta R is determining from the time delay expected from the radius luminosity. Well, the point is that this the tau is considered here to estimate the delta R. So the black hole mass, we need black hole mass to estimate the m dot parameter, and here we have a self-correlation. So there is a problem, and we have to look for other kind of parameter completely independent. And the most best candidate could be the iron 2. For a long time, and also in the previous talk and in the SWIAM's talk, we have learned that the RFE is one of the most important ions in the VLR. And also the eigenvector 1 has shown that RFE evolves in this sequence. So basically, the objects that are located in this zone corresponds to the stronger Fe2 emitters. But also in these regions, we can find the high accretor sources. So there is a clear correlation between the RFE and the Eddington radio, or this parameter m dot. In this plot is showing the correlation between both parameters, and we can see that, well, they are very well correlated. So taking this idea, Puddu and Professor Wang try to estimate this parameter delta R, but this time not consider the Eddington radio or the m dot. This time they correlate with this parameter RFE. So here you can see that, of course, there is also a correlation. Probably it's not so strong. The correlation coefficients indicate that there is a moderate relation, but also it can be used. So if we correct now, or we include this parameter delta R in the radius luminosity relation, so they can correct basically, and you can see here that the scatter decrease compared with this diagram like this. The potential result, or the most important result about this, is that RFE is completely independent. So we don't have to be scared about cell correlation or something like that. But RFE is not the only parameter that is probably related with the accretion rate. There are, for a long time, we know that the calcium-2 in the near infrared, emitted in the near infrared, basically this is a triplet. The calcium-2 in the near infrared is related with the optical Fe2. So here I am showing a comparison between the two ions. So this is for the Fe2. You can see that it's basically a lot of transition and is so complicated. But the calcium-2 is a simpler ion. It can be modeled like a 5-atom level. So in many sense, a calcium-2 is more simpler and more convenient for work with this ion. That's why at the end of the 80s, the people considered these ions to try to simulate or determine the properties of the Fe2, because it's easier. So this time we tried to collect all the samples with the calcium-2 and optical Fe2 measurements. And we got 58 sources. And this is how is the behavior of our samples. So you can see that we have basically bimodal behavior. We have a low redshift and low luminosity sources, and in the other case we have the opposite. And also here we have some windows that we have to fill in, but of course calcium-2 have some constraints because it is emitting at the beginning of the near infrared. So in the G band we have a lot of contamination by telluric lines, so there are some zones that really we never can be observed, but well, so this is the sample that we have. We cannot do anything else. Okay, so if we correlate the RFE and also the AirCat, well, they show a really very clear trend that also we use to determine the physical properties in the SWIAM's paper. Well, so here I am, since we have to determine exactly the relation and also the potential use of the calcium, the relation with the calcium and the Eddington radio or the m dot, we try to determine the different, how this, the behavior of this line with respect to this other parameter. So one interesting point that we have is the Baldwin effect. basically the Baldwin effect is the relation, an anti-correlation between the equivalent width and the luminosity of the line. It was first observed in the carbon-4, but basically it is present in all the emission lines. There is no clear explanation about what this effect. Some people have suggested that also it depends of the SED, has some metallicity effect. It could be also some column density. So there are like many explanations, but really there are no some clear. Since in our sample, we have like a bimodal behavior and some bias can be there, we decide to divide our sample in two based on the median luminosity. So green colors are basically low luminosity and blue colors are high luminosity. So the first column is the classical Baldwin effect. So you can see here the colors of the line indicate the fitting, consider the full sample or the divided samples. And you can see here that only we have significant correlation for H beta and also for the calcium 2. For the Fe2, well, we don't have anything, and for the oxygen 1 is basically flat. Also, we plot the black hole mass, but the most interesting result is with the Eddington radio. When we observe the behavior of the divided samples, we can see that for the calcium and also for the oxygen, the effect of the bias in luminosity disappear, especially for the H beta, the three lines share more or less the same slope. Also, in the case of the calcium 2, the three lines are still positive, but they also indicate very good the direction. In the case of the Fe2, we can see that there are some problems there. But some people have claimed that the direction of this relation, the slope, sorry, the direction of the slope can indicate that the emission lines are emitted in different regions. So for example, here the H beta is negative and calcium is positive, so they are emitted in different regions. But Fe2 should have the same behavior. But in at least with this panel and this small sample, it's not defined. If we try to look for other kind of larger samples and try to observe the behavior, for example, from Dong et al., here is the Fe2 UV, and this is the optical. So there is no like a very clear trend, at least from the oxygen 1, we can think that probably it is positive. So if I include larger samples here and try to compare the behavior of the equivalent width and the Eddington radio, well, we get something like is still like close to 0, but really there are a large uncertainties with the Fe2. But the calcium 2, it's saying that, well, so I have a most good behavior than the Fe2. But what happened now if we try also to compare these two parameters, RFE, that it's basically the Fe2 weighted by the H beta, and also this parameter RCAT that is have the the same definition.
Mari, sorry, 5 minutes more.
Yes,
Sorry.
yes, I'm close. Okay, so if I compare here these parameters, RFE and RCAT with the Eddington radio and also M-dot, I forgot to mention in the previous plots that basically both parameters, these both representation of the accretion rate intensity have the same behavior, as you can see in this plot. So again, here we can see that the calcium 2 indicates a positive correlation, but the Fe2 we have a mess. So when I include new more objects here, we can see that also the slope is positive. The black dots are our small sample, and the other ones corresponds to these studies. Also here is compare the RFE in the UV, and also the slope is positive. So this previous result is saying that the slope should be positive. But with the RFE and this small sample, we cannot define that. But the interesting point is that calcium 2 is saying this fact since the beginning. So calcium 2, since it is an easier ion, it can be used as a proxy of the accretion rate intensity. So taking this idea, we try to include the calcium 2 in the radius luminosity relation as Purdue did last year. However, we have from our sample, we have only 14 sources with time delay measures. So basically, it's like it's really a very small sample. But in any case, we try to determine and try to apply this correction using this ion. Also, it's important to mention that mostly of the dots here or the sources included here are coming from the old paper, very old paper. So we know that probably we have a lot of uncertainties, but in any case, we try because okay, so here it's basically the radius luminosity relation. We can see there are some departures, but here we cannot see a very clear trend. But we try to correct also the relation, and this is the result. The scatter decrease, but well, there is no a very good decreasing in the scatter. So here, if we compare with the Pudu results in his project, they are using like 75 objects, and we are using only 14 sources. If we compare the scatter, so our results with the calcium-2 indicate that it's slightly higher, but at least it's promising that probably we can do it. So the summary is that since the calcium-2 is an easier ion, it can be used more easy as a proxy than as a proxy of the accretion rate intensity. So calcium-2 is offering potential results, but of course, new samples observing these ions are needed. So we already are working in a proposal for observe these ions and try to include these ions in this ion in new surveys. So we will see if calcium-2 can be used like that. So thank you very much.
Thank you, Marilori. Very nice and very interesting results. I know that it's a small sample, but big samples also starts from small samples. So I wish you good luck in this this direction, especially since new near infrared surveys are coming, and so we have to get ready with these investigations. So thank you very much for this very interesting talk. So I open the floor for questions. We have time for one or two questions. No question. I guess everybody are hungry. So, but it was a really nice session, and I want to thank all the speakers for this inspiring talk. And yeah, and my daughter is also saying that we need to stop. So if you heard this, so thank you very much, and we resume after the break at 3.